Welcome back to chapter 2. In this chapter, we're going to be looking at some functions, some polynomial functions. We're going to be finding the zeros of those functions. We're going to be looking at rational functions, and we're going to be solving for x in different equations and inequalities and that kind of thing. So we'll be starting out by looking at linear and quadratic functions and a little bit of modeling. Um, so these topics, there's a lot in these topics, but these are also topics that we have been doing for the past several years. So we're going to go through them and know that this is a review that you should be fairly familiar with this stuff. So our learning targets for today, we're going to be identifying polynomial functions, writing equations for linear functions, satisfying given conditions. I mean, you can't just say, oh, write an equation for a linear function. Okay, y equals x. No, you have to have slopes or has to go through certain points, things like that. Graph quadratic functions, analyze and write equations of linear and quadratic functions, and write the equations of given quadratic functions. So, polynomial functions. Now, polynomial functions, the definition looks like this. We have f of x equals some number times x to a power plus some number times x to a power plus some number times x to a power plus some number times x to a power. All the exponents are positive integers. And that's basically it. The numbers in front are called coefficients. The exponents themselves are called degrees. The highest degree is the degree of the polynomial. The leading coefficient is the number in front of that term. So if we had something like f of x equals 3x to the fourth plus 7x cubed minus 12x plus 2, this would be a fourth degree polynomial because the highest exponent is 4, and the leading coefficient would be 3 because that's the one in front of that value. The zero function, f of x equals 0, is a polynomial function, and it has no degree and no leading coefficient, and we'll see that actually right about now. So we have some names of polynomials. Names of polynomials, the zero function, f of x equals 0. It's no degree, it's the x-axis is all that is. The constant function, f of x equals a, that's a horizontal line, has a degree of 0. A linear function, f of x equals ax plus b, where, again, the slope can't equal 0. A can't equal 0 for any of these, because that would just take it down to the next lowest one. So, linear function, f of x equals ax plus b, and that has degree 1 because it's x to the first. Quadratic, f of x equals ax squared plus bx plus c, has degree 2. We could go up to cubic if we wanted to. A cubic function, f of x equals ax cubed plus bx squared plus cx plus d, where a can't equal 0, and that has a degree of 3. A quartic would be with a degree of 4. Quintic is a degree of 5, and we can keep going. They all have names, but generally speaking, after a cubic or quartic, we would just go like a 5th degree polynomial, a 6th degree polynomial, things like that. In fact, some people go with even quartic, like a 4th degree polynomial. Generally speaking, cubic you would name as a cubic though. So those are just polynomial functions. Again, naming it, finding leading coefficients, finding the degrees, things like that. Writing them in order, which would be from the highest degree down to the lowest degree, would be standard form. And you can't have anything funny in there. So again, like the exponents have to be positive integers, so they're whole numbers. And yeah, so let's focus. Let's look at some linear functions and their graphs. So for a linear function, is the graph is going to be a line. It's going to be what's called an oblique line or a slant line, not horizontal or vertical. Horizontal and vertical lines are not linear functions. A horizontal line is a constant function, and a vertical line isn't actually a function at all. So a linear function has to have a slope, and the slope can't be 0. It can't be undefined. Is a horizontal line still a line? Yes, but it's not a linear function because the degree is 0. A linear function has degree of 1. So what can we do with linear functions? We can find the equations of one. If we have 2 points, we can find the equation of a line. So the first thing we need to do is find the slope. And this would be the hardest way, like starting out with 2 points. You can start out with other stuff, and we'll actually be going through that. Like you could have a slope and a point. Well, we're about to find a slope. The first thing you need to do is find a slope. Our variable for slope is m. Do you know why the variable for slope is m? No? Neither does anyone else. And then it's y minus y over x minus x. So we can go negative 1 minus 3 over 3 minus 1. That would be a negative 1 minus 3 over 3 minus 1. So our slope, negative 1 minus 3 is negative 4 over 3 minus 1 is 2. So our slope here is negative 2. Then I would put it into point slope form, which is y minus the y point equals slope times x minus the x point. We have to choose a point. I choose to use this point. So we have y minus the y part of the point, 3, equals our slope, negative 2, times x minus the x part of the point, 1. That's the equation in point slope form. We don't usually leave it there. We want to get it into slope intercept form. So we're going to distribute that 2, y minus 3 equals negative 2x plus 2. Add the 3 over, y equals negative 2x plus 5. And that's the equation of our line in slope-intercept form. We can graph the line. So if we have a graph, if we have our 2 points, we could actually just plot the 2 points. If we have our equation, though, we can start at the y-intercept of 5, and then the slope is negative 2, so we go down 2 over 1, down 2 over 1, down 2 over 1. We could have gone up 2 and backwards 1. Notice the point 1, 3 is on here. Also 3, negative 1 is on here. Once we have a few points, you only really need 2. I'd put a third one on there just to make sure something horrible didn't happen. Any more, that just helps you draw the line, especially since I don't have a straight edge. I'm trying to draw on a computer here. I like having a bunch. But we would connect the dots using a straight line, arrows going each way, and that would be how to graph a linear function. I know that you guys have been doing this for the past few years because my algebra classes are actually doing this right now. Average rates of change. Average rates of change is something that is going to stay with you for at least another couple years because it's something that my calculus classes are actually working on right now. But it's not really a calculus topic. An average rate of change, the formula for it, is f of b minus f of a over b minus a. If this looks a lot like a slope, then you're right. It is just a slope. That's all the average rate of change is. A linear function has a constant slope, so the average rate of change is consistent regardless of anything. However, not every function is a linear function. A quadratic function, which we'll be discussing in just a minute, has a nice parabola shape. If we want to find the average rate of change from here to here, it's literally just the slope of the line connecting the 2 points. We would just subtract y minus y over x minus x. So what is the average rate of change? Well, as I'm driving to town from South Camino, my distance away from home is increasing, but it's not increasing at a constant amount. It's going to go slow for a little bit, and then I speed up, and then it'll slow down because I hit stop signs, and it speeds up and slows down, speeds up, and I end up getting there. And so my total distance up here, we're going to say that's the top, my total distance is 22 miles. Oh, so my average rate of change from the beginning to the end, I suppose would be like that. My total distance is 22 miles, and my total time is 30 minutes. And so the average rate of change would be the total change of y divided by the total change of x. So 22 divided by, I'm not going to divide by 30 because we don't usually measure in minutes. That's half an hour. So 22 divided by half an hour, my average rate of change is going to be 44 miles per hour. That's my average speed to get to town. Now, sometimes I'm going 50, sometimes I'm stopped, but the average speed is 44 miles an hour because I went 22 miles in half an hour. So that's what an average rate of change does. It doesn't pay attention to all the times you go above and below and above and below. It's just how much did the y change divided by how much did the x change. It's the slope of the line connecting the 2 points. Association, correlation, and linear modeling. This is something you'll see for a little bit too, because this is what my statistics class is doing right now. So, association, this is all from a scatter plot. We have x and y points, we plot them in dots, and we get a scatter plot. Association talks about the direction of the relationship. As one variable increases, does the other one, or does the other one decrease? So association can be either positive or negative. A correlation is how close to a linear relationship are the points. A correlation could be weak or strong. And we'll get a value to describe that as well. And then linear modeling is just the act of taking those data points and then coming up with an equation that describes them. Now, not perfectly, but it can describe the pattern. So, association and correlation. Here are some examples. So, these first two have a positive association. Notice that they're going upwards. If we were to draw a line of best fit, which would be the linear modeling part, it would have positive slopes. These two at the bottom have downward associations. They'd have downward lines of best fit. So those associations are negative. The first two, like the two on the left here, have strong correlations because they're pretty close to straight lines. These next two have weaker correlations because they're not as close to a straight line. We can still tell they're going up or down respectively, but it's not as definitive. And then this one at the end, it has little or no linear association. We can't even tell if it's going up or down. The correlation there would be 0 because the x value does not seem to affect the y value. Now, a couple things. Correlations can be a little bit tricky because that has a correlation of 0, but so would something like this, where the line is just horizontal. Even though it's a perfectly straight horizontal line, it would have a correlation of 0. So would something like this. Looks like a perfect quadratic, but is it going up or down? It's going up, then it's going down. That would have a correlation of 0 because correlation describes how close to a linear fit it is. Not how close to any fit, how close to specifically a linear fit. So we have the correlation coefficient, which is r, and that's the number that we can use to describe the correlation. This number is always between -1 and 1. When it's -1, or when it's either -1 or 1, it means that the points actually fall into a perfectly straight line. Like you took an equation, you found a table from the equation, and you graphed those points. And then 0, we talked about 0 up with those ones. When it's positive, r is positive. When it's negative, r is negative. And the strong linear correlation means that the absolute value is about equal to 1. And then when it's 0, there's a weak correlation. I will show you how to find this in a meet. You guys have already found this in previous years. You don't do it by hand. The equation is not pleasant. You do it with your calculator, or Desmos, actually. And the way we do it is we actually find the correlation by using the regression. It finds it for us. So regression is the act of making a line of best fit or a curve of best fit. In this case, since we're talking about linear functions, it would be a line. So these are the general steps, and we'll go over in more detail in class. But the general steps, we're going to enter and plot the data, so we make a scatter plot. Check for evidence of linearity, like especially if it's supposed to be linear, we want to make sure that it actually looks linear. Or if it's quadratic, or if it's cubic, like we want to look to see what shape does it look like, because that's what we want to do. We wouldn't want to try and put a line on a quadratic model, like that wouldn't work out. Find the regression model that fits the situation. And there are two different linear ones, especially in your calculator. Then graph the model on the scatter plot and to see how well it works. And then use the model to make predictions that the problem's asking for. You answer the question. These are the same 5 steps I have always used randomly. Like this actually just came straight from the book, but these are the exact same things. You enter the data, you graph the data, you do the regression, you graph the data again, you answer the question. Same exact steps. And we'll get into more details on how you actually do this stuff, depending on what technology you have in the class. Quadratic functions and their graphs. So we saw quadratic functions look like parabolas. They're the U shape. They could be positive, where they're going upwards or happy. They could be negative, in which case they're going down. They're sad faces. And that depends on that leading coefficient of the quadratic. Is it positive or negative? We have a couple forms of the quadratic equation. The first is the vertex form, and this actually comes directly from transformations of the parent function y equals x squared. So we've moved it over h and up k, which puts the vertex at h comma k. The axis of symmetry is x equals h, and let's see, we talked about if a is, so if the leading coefficient is positive, it opens up. If it's negative, it opens down. And so, but this is vertex form because it has the vertex in it. Standard form is this form. Standard form is that f of x equals ax squared plus bx plus c, where the vertex, the x part of the vertex is negative b over 2a. The y part of the vertex, we actually just have to plug it in. It doesn't tell us what it is in the equation itself, but we would plug it in to get h, and that's what this is saying right here, is that from the standard form, we could plug that in to get the vertex for the vertex form. And we can rewrite a standard form equation in vertex form. To go from vertex form to standard form, it's super easy. We would just square out the x minus something, which, like, x minus 2 squared is not x squared minus 2 squared. It would be x squared minus 4x plus 4. It's actually x minus 2 times x minus 2. So don't just try and distribute that squared. You actually have to multiply it out. But that's how you get to standard form from vertex form. Going the other way, we're going to do something called completing the square. So for this, the very first thing we need to do is we need to, we're going to move this constant over to the other side for a few moments. So we'll have f of x plus 5 equals negative 3x squared plus 6x. And now we need the x squared to be by itself, so we're going to factor out a negative 3 from both of those two terms. Even if the x term doesn't have that factor, we'd still need to factor it out. It's part of the process. F of x plus 5 equals negative 3 times x squared minus 2x. And then I'm going to leave a little bit of a space there. And now we will get to the completing the square step. So we'll have negative 3, and then we'll have something squared. And so what we do, the x squared, that'll just become an x. Then we're going to take this number, and we're going to divide by 2. It's always 2, even though that's a 2, that's coincidental. So negative 2 divided by 2 is minus 1. And then from there, we need to square that number and put it up here. Negative 1 squared is plus 1. Now, this x minus 1 squared that we have in that bottom step, if we actually squared it out, it would equal x squared minus 2x plus 1. That's why we have to put that 1 up there, so that the actual factor form is true. Now, can we go around adding 1 wherever we feel like it, all willy-nilly like, to an equation? No, we have to do the exact same thing to the other side. The problem, though, here is that we didn't just add 1. We added 1 times that negative 3. So we actually added negative 3 to this side of the equation, which means we need to add negative 3 to that side of the equation as well, which It's not going to change the f of x. However, negative 3 plus 5 is plus 2, which we can now move back over to the other side of the equation to get f of x equals, that's 2 equal signs there, that was fun, negative 3 times x minus 1 squared minus 2. The vertex is going to be at 1, 2. The axis of symmetry will be x equals 1. That's just the x part of the vertex, x equals 1. But that's how we can write in vertex form an equation that came to us in standard form. Standard form is easier for solving sometimes. Sometimes vertex form is actually pretty easy to solve. Vertex form is usually easier to graph. Standard form is easier to find the zeros sometimes. And so that is the quadratics. We do have a little bit extra. Oh, I shouldn't have put the vertex down there. A quick couple formulas that we use with quadratics that are common enough that you want to know the formula for them. And that would be the free fall formula. So you take an object, you just drop it. This one actually includes it includes initial velocity and initial height, but these are formulas that we use if we have something that's being like thrown or kicked, something where gravity is affecting them. So the distance, that's s of t, is going to be negative 1/2 times gravity times t squared plus v naught, that's the initial velocity, times time, plus s naught's the initial height. Then the velocity is negative g times t plus v naught, the initial velocity. Now, a lot of these are going to be problem specific. G, however, in either of these two equations is going to be the force of gravity. On Earth, that is going to be fairly constant. I mean, it does fluctuate a little bit, but we keep it constant for what we do. So gravity is either 32 feet per second squared, if you're giving your stuff in feet, but it turns out that other places in the world also are affected by gravity, and they use the metric system. So 9.8 meters per second squared is what it would be if you're given stuff in meters. So it's important to look at what units your problem is in so that you use the right number. And then that number itself is just the acceleration due to gravity, and it's constant. So that is a quick recap on linear equations, polynomials, quadratic equations, a little bit of modeling. I'll show you how to model with quadratics as well when we're looking at modeling with linear functions. And so again, quick recap, but this is stuff that you have seen a few times at this point, so it shouldn't be too horrible. And I will see you in class where we can look at some technology, but until then, keep working problems, keep asking questions, and as always, happy mathing.